and 9-2 on Wednesday, and those are our only 2 new sections of the week. So you guys will have a little bit of time here and there to work on projects and Math Excel and that sort of thing. All right, so this chapter is just kind of a short little 2-section interlude, we'll call it. It's just over 9.1 and 9.2. It's all about correlation, correlation coefficients, lines of best fit. This section is pretty much over all of our correlation and correlation coefficients, which you may have talked about before in previous math classes a little bit. If you did in previous math classes, you probably used technology to calculate lines of best fit and correlation. We're going to do it with technology and, of course, without technology as well. Okay, so first we're going to start with what is correlation. Correlation is a relationship between 2 variables. It's generally our trend in the data. Of course, X is our independent variable and Y is our dependent variable. We also can see these words explanatory and response. You might see those used instead of independent and dependent, but it means the same thing. When we're looking at scatter plots, 2 variables graphed together, we can see the following trends. If one variable goes up and the other one goes down, which will look like in general the graph going down from left to right, we say that it is a negative linear correlation. Negative because it's going down, linear because we can use a line to describe the general trend in that data. If one variable goes up as the other goes up, our graph will look like it's increasing from left to right, and we say that is a positive linear correlation. If our data is all over the place and we can't use any sort of line or curve to describe the trend, we say that there is no correlation in the data, the one on the bottom left there. And then occasionally we will see data that has a trend, has a correlation, but it isn't linear. It doesn't make a line. It looks something like that, for example. That is one we would call a quadratic correlation. If you guys remember parabolas from like back in the day, we don't get too much into those other types. All we say is if there's a correlation but it's not linear, we just say non-linear correlation. Okay, but in previous math classes, you might have done like quadratic or cubic or exponential regression. Those are all other ways that we can see trends in data other than linear data. Okay. All right, so we need to be able to calculate correlation and interpret it, and we use an R value to do that. R comes from, well, let me start with this actually. So it looks like a lowercase p. It's actually the Greek letter rho. That is a population correlation coefficient. So if you have population data and you want to calculate the correlation of it, you use rho. And it looks like a letter P because it's a Pearson correlation coefficient. That's why they use the letter P. That's the guy who figured this out. R is the one that we see more often, and that is a sample. So if we have a sample of data, we use R to calculate the correlation. We call it the correlation coefficient. Now the formula itself is in your purple packet. You can see here there's a lot of summation. So this is going to involve a table of values. We're going to set up the table of the columns like we've done before with like standard deviation problems. We're going to sum them all up, and those sums at the bottom of the table are ultimately going to be the numbers that we're plugging into this formula, which we'll do in a little bit. Okay, so what does R mean? So R, first of all, will be a range of numbers between -1 and +1. If you get anything outside of that, you calculated it incorrectly. -1 means it is a perfect negative correlation, meaning if you look at that data, it is making a perfect line. Every dot hits the line going down from left to right, okay? And +1 is a perfect positive correlation, meaning the data makes a perfect line going up from left to right. 0 is right in the middle. 0 means no correlation. Or if you have an R that's close to 0, we say no correlation. Like if it's 0.1 or 0.2 or -0.1 or -0.2, those would all be no correlation. If we have something closer to 1 or -1 on those ends of the scale, we say it's a strong correlation, either strong positive if it's a positive number or strong negative if it's a negative number. And when we say close, that's where it's like kind of open to interpretation a little bit. I would say if it's like a 0.7 or higher, 0.7, 0.8, 0.9, then you're going to have a strong correlation. If it's less than that, like 0.3 to 0.6, it's going to be weak.
Hello. Can I see Richardson and Noski?
Yes.
Rich, 30 seconds. Zach and Olivia. Come on down.
All right. Okay, so what I need you to do On the next slide you have on your paper, we're going to put some letters here. A, B, C, D, E, F. This is a little matching problem. So you're going to take each graph and see if you can match its R value, its correlation coefficient, and the description of its correlation. Okay, so match both of those up. I'll give you a few minutes and then we'll check our answers. Make sure you match up both of them, the number and the description. Okay, when you're ready, here are our answers. E and F are really similar. F, the data is clustered a little bit more towards where you would draw a line of best fit. So we say F has a little bit stronger of a correlation, so closer to 1 than E. E, it's a little more spread out. Still positive, still trending up, but a little more spread out there. Okay. Any questions on this? Oh, one of them was wrong. Hold on. C and D, did I write them out? Strong negative. Oh yeah, perfect negative. Thank you. Some of you were giving me eyeballs. I figured, so feeling I did something wrong there. There we go. Okay. Any questions other than that? No? Okay, good. All right, so let's calculate one of these. The next slide you have on there is kind of the setup. Like I said, it's just a whole bunch of summations. I think it's actually easier than what we did with standard deviation before, because literally you're just going to take every single column, sum up every single column, and those numbers at the bottom you're going to use in the formula. Then when you plug it in, you don't have to worry about which summation is the one you want, because you want all of them. So X and Y is going to be our original data. And then you're just going to add up all those. Then you're going to have X times Y, X squareds, Y squareds, add all those up. And then we're plugging them into the formula that you see here. The only other thing you need in the formula that will not be in the table is N. N is the number of points that you have. So if you have 5 sets of coordinates, N is 5. That's all you have to worry about. And then we plug it in our calculator and simplify. So pretty straightforward. All right, so let's do one on the back. All right, so here we are comparing number of years out of school, which is X, and then annual contribution in thousands of dollars, which is Y, and they have nicely filled those two columns in for us already. Okay, so 3 other sets of information we need to do. We need to do all the X times Y, so we need to take all the X's and square them, we need to take all the Y's and square them, and then we need to add up all 5 columns. So this will take a couple minutes, just all in your calculator. All right. Let's see. 12.5, 87, 73, double check I don't make a calculator mistake. Hopefully somebody else is fact checking this for me. 29.7, 74.4, and 81. Okay, all my X's and square them. 1, 100, 25, 225, 9, 576, and 900. All my Y's and square them. I'm not going to round until the very end here. 156.25, 75.69, 213.16, 27.04, 98.01, 9.61, 7.29. Okay. And then I got to add them all up. All right, 88 for that sum. $56.7 for that one. $435.6. $18.36. Last one is 587.05. I think that's what I got in first period. Okay. Only other thing I don't have on here is n. N in this problem is 7. There are 7 coordinates that we have. Okay. All right, let me write my formula down. So my R value is the following. N times the sum of xy minus the sum of x times the sum of y. Then I've got 2 square roots in the bottom, one for my x's, one for y y's. N times the sum of x squared minus the sum of x squared. N times the sum of y squared minus the sum of y squared. There we go. Okay. Filling it in. Again, n is 7. The sum of x times y is 435.6 for us, minus the sum of my x's, 88, times the sum of my y's, 56.7. So you could put each of those in their own parentheses if you want to. You could put them in a double parentheses if you want to. That's up to you. Even like that, maybe. Okay. Denominator, 7 times. Now this is where you have to be careful. So this sum of x squared is different than this sum of x squared. So I'm going to start with the one with the parentheses. You got to think order of operations with these. If I'm looking at a parentheses, I do the parentheses first. So this tells me sum up all my x's first, which is 88, and then we square that number. Versus when I look at this one, I take all of my x squareds first. You can think of the x squared as being in a parentheses. And then I sum that up. So this one is going to be that sum of x squared column on the far side. Okay, so this is the sum of all our x's squared. This is the sum of our x squareds. Okay, and then the y's are going to be similar. So for that first one, it's going to be 7 times 1836 minus 88 squared. And for the second one, it's going to be 7 times 587.05 minus the sum of my y's, 56.7 squared. Okay, then we're just going to do numerator and denominator separately. Divide last. You should be able to, in either this calculator or the red calculator, just type the lines in all at once. So on top, 435.6 times 7 minus 88 times 56.7, get negative 1940.4. On the bottom, times square root 7, 587.05 minus 56.7 squared. 2137.499. And then we divide last. And I get negative 0.9078. And that's our R that we're looking for. Remember, your number should be between -1 and +1. If it's outside of that range, you did something wrong. So I would check those summations probably at the top first. So can you tell me what that means about the correlation? Strong, because it's close to -1, negative, because it's negative. And then I would even add one more word here, linear correlation. Okay. We only probably wouldn't put linear if we were asked if it's linear or non-linear. We might say there's no linear correlation or weak linear correlation, but we want to specify that this is all linear that we're looking at. Okay. Any questions getting R? All right, so not difficult calculations here, just a little timely to get to it. Okay. Last thing, well, actually two last things we're going to do. Let's check it in the calculator. Let me show you how to do that. This will be especially helpful in your Math Excel. Go ahead into Stat Edit and put this data in there in your L1 and your L2. Stat and then Edit. Go up to the list name, hit clear, go back down. Get it all in there. The other thing we want to check real quick is we want to make sure that your stat diagnostics, which is what's going to give us the R, are turned on. So to make sure they're turned on, if you go into mode, you can go down to the bottom where it says stat diagnostics, and it should say stat diagnostics is on. If it doesn't say on, go down to the word on and select it to turn it on. Okay. So data in L1 and L2, under mode, stat diagnostics needs to be on. Okay. All right, once you've done those two things, we're going to hit stat. We're going to go over to calculate. We've used this a lot, those one variable statistics. Once you get past number 3, all of the ones below that, the REGs, these are regressions that you can use, which are correlations that we can look at. Like I said before, there's other ones, quadratic, cubic, things like that, but we are dealing only in linear regression, linear correlation. So we're going to choose option number 4. Okay, and then it should tell you your X is list 1 and your Y is list 2. That should be the default. Go down, hit calculate, and then it spits out a few things, but we're concerned about the R value, which you can see negative 0.9078. That's what we found. Okay, so you can check that answer pretty easily if you want to. It also gives you an A and a B. A and B are the slope and y-intercept of the line of best fit, which is what we're going to do in section 9 too. It's a very similar type of calculation, but we're going to calculate that slope, calculate that y-intercept to get the line of best fit by hand. If you want to see the graph, which in Math Excel you might have to like match a scatter plot, you can do it by hand if you want to. But if you go to y equals, make sure your plot is turned on. So if there's anything in there, clear it out. Go up to plot 1, hit enter, go back down. That'll turn your plot on. And then you need to do this every time. You need to zoom in on the particular set of statistics you have in your lists. So you're going to hit zoom and then number 9, zoom stat. And that'll give you a really nice scatter plot of whatever data you have in your lists. Okay, and then eventually we'll put the line of best fit in there too and see it like superimposed in this picture. Okay, any questions on the graphing calculator, checking correlation coefficient, getting the scatter plot? Everybody get it to show up okay? Okay. Last but not least then for our lesson is once we have a correlation coefficient, we can use a table of values to determine if it's significant, meaning the relationship between the variables is significant, is ultimately what we're trying to figure out if there's a correlation. The table that you want, this is what you need your purple packet for. It is the last page of your purple packet. It says table 11. It is critical values for a Pearson correlation coefficient, very last table. There are two things that you need to use this table. You need n, which is the number of pairs of data that you have, and then you need alpha, the Greek letter alpha, which is a level of significance. Alpha will be given to you, and we'll talk more about alphas in later chapters, but for right now, just know that it's a value that's going to be given to you, and that's the level of significance that is used for that particular problem. Okay, how this works: if the absolute value of R is greater than the critical value that you find on your chart in the middle of it, then we say that the correlation is significant. If it is not greater than the critical value, then we say that the correlation is not significant. Saying it's significant, again, tells us that there's some sort of relationship between those variables. If it's not significant, it's telling us we don't have enough information. There might not be enough points, or there might not be enough evidence in the numbers themselves to show that we have a relationship. Okay, so let's do it for the last problem that we just had. Our R value was negative 9078. Okay. The next thing we need to figure out is the critical value from our chart. So to get the critical value, they're telling us use an alpha of 0.05, and remember our n for the last problem was 7. Okay, so we're going to pretty much find where those intersect on our chart. We're going to find n is 7, we're going to find alpha is 0.05, and then we're going to look in that particular row and column, and you should see a critical value of 0.754. Okay, so now we want to compare the two. The absolute value of R, 0.9078, we're going to compare to 0.754. In this case, the absolute value of negative 0.9078 is greater than 0.754. So we can then say there is enough evidence to say the correlation is significant. If it was less than, we would say there is not enough evidence to say the correlation is significant. Okay, so it's either is or is not in that last statement. That's all you've got to worry about. And that is it for our lesson today. You have an exit ticket that you're going to complete. You can work together if you want on it. You're definitely going to need your calculators. It's one R value that you're calculating. Table's all set up for you. Put it in the tray when you're done. And then the rest of the period is yours to work. You can work on your project, or you can work on your Math Excel. Tomorrow there is no new lesson. It's Pi Day tomorrow. So we're going to do a fun little origami activity for Pi Day. Just take a little break. And then you guys will have again work time if you want it. And then we'll finish up this chapter on Wednesday with mine too. Okay? Go. 1, 2, 3. Yep. Math Excel is due on Wednesday nights. Math Excel is due on Wednesday nights.